We'll begin our foray into networking by reviewing the history of the Internet and its design principles. Networking today is an eclectic mix of theory and practice, in large part because the early Internet architects set out with clear goals and allowed flexibility in achieving them.
With all that flexibility, does that mean we'll see the rollout of IPv6 soon?
Only in your dreams. In this lesson, we will cover a brief history of the Internet. The Internet has its roots in the ARPANET, which was conceived in 1966 to connect big academic computers together. The first operational ARPANET nodes came online in 1969 at UCLA, SRI, UCSB, and Utah. Around the same time, the National Physical Laboratory in the UK also came online. By 1971, there were about 20 ARPANET nodes and the first host-to-host protocol. There were 2 cross-country links, and all of the links were at 50 kbps. Here is a rough sketch of the ARPANET as drawn by Larry Roberts in the late 1960s. And you can see the 4 original nodes here, as well as some other well-known players, such as Berkeley, the Mac project at MIT, BBN, Harvard, Carnegie Mellon, Michigan, Illinois, Dartmouth, Stanford, and so forth. This is what the ARPANET looked like in the late 1960s. Here's a picture of the ARPANET in June 1974, and you can see not only some additional networks that have come online, but also a diagram of the machines that are connected at each of the universities. You can also see a connection here between the ARPANET and NPLnet. Of course, the ARPANET wasn't the only network. There were other networks at the time. SatNet operated over satellite, there were packet radio networks, and there were also Ethernet local area networks. Work started in 1973 on replacing the original network control protocol with TCP/IP, where IP was the internetwork protocol and TCP was the transmission control protocol. TCP/IP was ultimately standardized from 1978 to 1981 and included in Berkeley Unix in 1981. And on January 1st, 1983, the Internet had one of its flag days, where the ARPANET transitioned to TCP/IP. Now, the Internet continued to grow, but the number of computers on the Internet really didn't start to take off until the mid-90s. You can see here that around August 1995, there were about 10 million hosts on the Internet, and 5 years later, there was an order of magnitude more hosts on the Internet, more than 100 million. During this period, the Internet experienced a number of technical milestones. In 1982, the Internet saw the rollout of the domain name system, which replaced the host.txt file containing all the world's machine names with a distributed name lookup system. 1988 saw the rollout of TCP congestion control after the net suffered a series of congestion collapses. 1989 saw the NSFNet and BGP interdomain routing, including support for routing policy. The 90s, on the other hand, saw a lot of new applications. In approximately 1992, we started to see a lot of streaming media, including audio and video. The web was not soon after in 1993, which allowed users to browse a mesh of hyperlinks. The first major search engine was AltaVista, which came online in December of 1995. And peer-to-peer protocols and applications, including file sharing, began to emerge around 2000. Now, today's Internet is experiencing considerable problems and growing pains, and it's worth bearing some of these in mind and thinking about them, as many of them give rise to interesting research problems to think about as we work through the material in the course. One of the major problems is that we're running out of addresses. The current version of the Internet protocol, IPv4, uses 32-bit addresses, meaning that the IPv4 Internet only has 2 to the 32 IP addresses, or about 4 billion IP addresses. Furthermore, these IP addresses need to be allocated hierarchically, and many portions of the IP address space are not allocated very efficiently. For example, the Massachusetts Institute of Technology has 1/256 of all of the Internet address space. Another problem is congestion control. Now, congestion control's goal is to match offered load to available capacity. But one of the problems with today's congestion control algorithms is that they have insufficient dynamic range. They don't work very well over slow and flaky wireless links, and they don't work very well over very high speed intercontinental paths. Now, some solutions exist, but change is hard, and all solutions that are deployed must interact well with one another. And deployment, in some sense, requires some amount of consensus. A third major problem is routing. Routing is the process by which nodes on the Internet discover paths to take to reach another destination. Today's interdomain routing protocol, BGP, suffers a number of ills, including a lack of security, ease of misconfiguration, poor convergence, and non-determinism. But it sort of works, and it's the most critical piece of the Internet infrastructure in some sense because it's the glue that holds all of the Internet service providers together. Another major problem in today's Internet is security. Now, while we're reasonably good at encryption and authentication, we are not actually so good at turning these mechanisms on, and we're pretty bad at key management, as well as deploying secure software in secure configurations. The fifth major problem is denial of service. Now, the Internet does a very good job of transmitting packets to a destination, even if the destination doesn't want those packets. This makes it easy for an attacker to overload servers or network links to prevent the victim from doing useful work. Distributed denial of service attacks are particularly commonplace on today's Internet. Now, the thing that all of these problems have in common is that they all require changes to the basic infrastructure. And changing basic infrastructure is really difficult. It's not even clear what the process is to achieve consensus on changes. So as we work our way through the course, it will be interesting to see the problems that we encounter in each of these areas, various solutions that have been proposed, and also to think about ways in which new protocols and technologies can be deployed. In later parts of the course, we'll learn about a new technology called software-defined networking, or SDN, that makes it easier to solve some of these problems by rolling out new software technologies, protocols, and other systems to help manage some of these issues. In this lecture, we will talk about the Internet's original design principles. These design principles were discussed in the paper reading for today, The Design Philosophy of the DARPA Internet Protocols by Dave Clark, dated 1988. The paper has many important lessons, and we will go through many of them as we revisit many of the design decisions. Before we jump into any details, let's talk about some of the high-level lessons. One of the most important conceptual lessons is that the design principles and priorities were designed for a certain type of network. And as the Internet evolves, we are feeling some of the growing pains of some of those choices. In the last lesson, we talked about a number of the problems and growing pains with the Internet. And it's worth bearing in mind that many of the problems that we are seeing now are a result of some of the original design choices. Now, that's not to say that some of these design choices are right or wrong, but rather that they simply reflect the nature of our understanding at the time, as well as the environment and constraints that the designers faced for the particular network that existed at that time. Now, needless to say, some of the technical lessons from the original design have turned out to be fairly timeless. One concept is packet switching, which we will discuss in this lesson, and another is the notion of fate sharing, or soft state, which we will discuss in a subsequent lesson in the course. The fundamental design goal of the Internet was multiplexed utilization of existing interconnected networks. There are two important aspects to this goal. One is multiplexing, or sharing. So one of the fundamental challenges that the Internet's technologies needed to solve was the shared use of a single communications channel. The second major part of this fundamental goal is the interconnection of existing networks. These two subproblems had two very important solutions. Statistical multiplexing, or packet switching, was invented to solve the sharing problem, and the narrow waist was designed to solve the problem of interconnecting networks. Let's talk about each of these now in turn. We'll first talk about packet switching. In packet switching, the information for forwarding traffic is contained in the destination address of every datagram or packet. Similar to how you would write a letter and specify the destination to where you want the letter sent, and that letter might wend its way through multiple intermediate post offices en route to the recipient, packet switching works much the same way. There is no state established ahead of time, and there are very few assumptions made about the level of service that the network provides. This assumption about the level of service that the network provides is sometimes called best effort. So how does packet switching enable sharing? Just as if you were sending a letter, many senders can send over the same network at the same time, effectively sharing the resources in the network. A similar phenomenon occurs in packet switching when multiple senders send network traffic or packets over the same set of shared network links. Now this is in contrast to the phone network, where if you were to make a phone call, the resources for the path between you and the recipient are dedicated and are allocated until the phone call ends. The mode of switching that the conventional phone network uses is called circuit switching, where a signaling protocol sets up the entire path out of band. So this notion of packet switching and statistical multiplexing, allowing multiple users to share a resource at the same time, was really revolutionary, and it is one of the underlying design principles of the Internet that has persisted. Now, an advantage of statistical multiplexing of the links in the network means that a sender never gets a busy signal. The drawbacks include things like variable delay and the potential for loss or dropped packets. In contrast, circuit switching provides resource control, better accounting, and reservation of resources, and the ability to pin paths between a sender and receiver. Packet switching provides the ability to share resources and potentially better resilience properties. Let's take a quick quiz on packet switching versus circuit switching. Which of the following are characteristics of packet switching and circuit switching? Variable delay, busy signals, sharing of network resources, like an end-to-end path, among multiple recipients, and dedicated resources between the sender and receiver. Each of these options only has one correct answer. Variable delay is a property of statistical multiplexing or packet switching. Circuit switch networks can have busy signals. Packet switch networks share network resources, and circuit switch networks typically have dedicated resources along a path between the sender and receiver. Let's now take a look at the second important fundamental design goal of the Internet, interconnection, and how interconnection is achieved with a design principle called the narrow waist. Let's keep in mind that one of the main goals was to interconnect many existing networks and to hide the underlying technology of interconnection from applications. This design goal was achieved using a principle called the narrow waist. The Internet architecture has many protocols that are layered on top of one another. At the center is an interconnection protocol called IP, or the Internet Protocol. Now, every Internet device must speak IP, or have an IP stack. Given that a device implements the IP stack, it can connect to the Internet. This layer of the network is sometimes called the network layer. Now, this layer provides guarantees to the layers above. On top of the network layer sits the transport layer. The transport layer includes protocols like TCP and UDP. The network layer provides certain guarantees to the transport layer. One of those guarantees is end-to-end connectivity. For example, if a host has an IP address, then the network layer, or IP, provides the guarantee that a packet with that host destination IP address should reach the destination with the corresponding address with best effort. On top of the transport layer sits the application layer. The application layer includes many protocols that various Internet applications use. For example, the web uses a protocol called the Hypertext Transfer Protocol, or HTTP, and mail uses a protocol called SMTP, or Simple Mail Transfer Protocol. Transport layer protocols provide various guarantees to the application layer, including reliable transport or congestion control. Now, below the network layer, we have other protocols. The link layer provides point-to-point connectivity, or connectivity on a local area network. A common link layer protocol is Ethernet. Below that, we have the physical layer, which include protocols such as SONET for optical networks, and so forth. The physical layer is sometimes called Layer 1, the link layer is sometimes called Layer 2, and the network layer is sometimes called Layer 3. We tend to not refer to layers above the network layer by number. The most critical aspect of this design is that the network layer essentially only has one real protocol in use, and that's IP. That means that every device on the network must speak IP, but as long as the device speaks IP, it can get on the Internet. This is sometimes called IP over anything or anything over IP. Now, the advantage to the narrow waist, as I mentioned, is that it's fairly easy to get a device on the network if it runs IP. But the drawback is that because every device is running IP, it's very difficult to make any changes at this layer. However, people are trying to do so, and later in the course, when we discuss software-defined networking, we will explore how various changes are being made to both the IP layer and other layers that surround it. So we've talked about how the Internet satisfies the goals of sharing and interconnection, and now let's talk about some of the other goals that are discussed in the DARPA design philosophy paper. As we discuss some of these other goals, it's worth considering and thinking about how well the current Internet satisfies these other design goals in the face of evolving applications, threats, and other challenges. One of the goals discussed is survivability, which states that the network should continue to work even if some devices fail or compromised, and so forth. There are two ways to achieve survivability. One is to replicate, so one could keep state at multiple places in the network, such that when any node crashes, there's always a replica or a hot standby waiting to take over for the failure. Another way to design the network for survivability is to incorporate a concept called fate sharing. Fate sharing says that it's acceptable to lose state information for some entity if that entity itself is lost. For example, if a router crashes, all of the state on the router, such as the routing tables, are lost. If we can design the network to sustain these types of failures, where the state of a particular device shares the fate of the device itself, then we can withstand failures better. So fate sharing makes it easier to withstand complex failure scenarios, and engineering is also easier. Now, it's worth asking whether the current Internet still satisfies the principle of fate sharing. In a subsequent lesson, we'll talk about network address translation and how it violates the notion of fate sharing. There are other examples where the current Internet's design violates fate sharing, and it's worth thinking about those. The Internet supports heterogeneity through the TCP/IP protocol stack. TCP/IP was designed as a monolithic transport where TCP provided flow control and reliable delivery, and IP provided universal forwarding. Now, it became clear that not every application needed reliable in-order delivery. For example, streaming voice and video often perform well even if not every packet is delivered. And the domain name system, which converts domain names to IP addresses, often also doesn't need completely reliable in-order delivery. Fortunately, the narrow waist of IP allowed the proliferation of many different transport protocols, not just TCP. The second way that the Internet's design accommodates heterogeneity is through a best effort service model, whereby the network can lose packets, deliver them out of order, and doesn't really provide any quality guarantees. It also doesn't provide information about failures, performance, etc. On the plus side, this makes for a simple design, but it also makes certain kinds of debugging and network management more difficult. Another goal of the Internet was distributed management, and there are many examples where distributed management has played out. In addressing, we have routing registries. For example, in North America, we have ARIN, or the American Registry for Internet Numbers. And in Europe, that same organization is called RIPE. DNS allows each independent organization to manage its own names, and BGP allows each independently operated network to configure its own routing policy. This means that no single entity needs to be in charge, and thus allows for organic growth and stable management. On the downside, the Internet has no single owner or responsible party. And as Clark said, some of the most significant problems with the Internet relate to the lack of sufficient tools for distributed management, especially in the area of routing. In such a network where management is distributed, it can often be very difficult to figure out who or what is causing a problem. And worse, local actions such as misconfiguration in a single local network can have global effects. The other three design goals that Clark discusses are cost-effectiveness, ease of attachment, and accountability. It's reasonable to argue that the network design is fairly cost-effective as is, and current trends are aiming to exploit redundancy even more. For example, we will learn about content distributions and distributed web caches that aim to achieve better cost effectiveness for distributing content to users. Ease of attachment was arguably a huge success. IP is essentially plug and play. Anything with a working IP stack can connect to the internet. There's a really important lesson here, which is that if one lowers the barrier to innovation, people will get creative about the types of devices and applications that can run on top of the internet. Additionally, the narrow waist of IP allows the network to run on a wide variety of physical layers, ranging from fiber to cable to wireless and so forth. Accountability, or the ability to essentially bill, was mentioned in some of the early papers on TCP/IP, but it really wasn't prioritized. Datagram networks can make accounting really tricky. Phone networks had a much easier time figuring out how to bill users. Payments and billing on the internet are much less precise, and we'll talk about these more in later lectures. It's also worth noting what's missing from Clark's paper. There's no discussion of security, there's no discussion of availability, there's no discussion of mobility or support for mobility, and there's also no mention of scaling. There are probably a lot of other things that are missing, and it's worth thinking about on your own some of the other things that current internet applications demand that are not mentioned in Clark's original design paper. So as a quick quiz, can you quickly check all of the design goals in the list that were mentioned in Clark's original design goals paper? Security, support for heterogeneity, support for interconnection, support for sharing, and support for mobility. Clark's original design goals paper mentions the need to support heterogeneity, interconnection, and sharing. In this lesson, we'll cover the end-to-end argument as discussed in the paper End-to-End Arguments in System Design by Salzer, Reed, and Clark in 1981. In a nutshell, the end-to-end argument reads as follows. The function in question can completely and correctly be implemented only with the knowledge and application standing at the endpoints of the communication system. Therefore, providing that question function as a feature of the communication system itself is not possible. Essentially, what the argument says is that the intelligence required to implement a particular application on the communication system should be placed at the endpoints rather than in the middle of the network. Commonly used examples of the end-to-end argument include error handling and file transfer, encrypting end-to-end versus hop-by-hop in the network, and the partition of TCP and IP of error handling, flow control, and congestion control. Sometimes the end-to-end argument is summarized as the network should be dumb and minimal, and the endpoints should be intelligent. Many people argue that the end-to-end argument allowed the internet to grow rapidly because innovation took place at the edge in applications and services rather than in the middle of the network, which can be hard to change sometimes. Let's look at one example of the end-to-end argument, error handling and file transfer. Let's suppose that computer A wants to send a file to computer B. The file transfer program on A asks the file system to read the file from the disk. The communication system then sends the file, and finally, the communication system sends the packets. On the receiving side, the communication system gives the file to the file transfer program on B, and that file transfer program asks to have the file written to disk. So what can go wrong in this simple file transfer setup? Well, first, reading and writing from the file system can result in errors. There may be errors in breaking up and reassembling the file, and finally there may be errors in the communication system itself. Now, one possible solution is to ensure that each step has some form of error checking, such as duplicate copies, redundancy, timeout and retry, and so forth. One might even do packet error checking at each hop of the network. One could send every packet 3 times. One might acknowledge packet reception at each hop along the network. But the problem is that none of these solutions are complete. They still require application-level checking. Therefore, it may not be economical to perform redundant checks at different layers and at different places of this particular operation. Another possible solution is an end-to-end check and retry, where the application commits or retries based on a checksum of the file. If errors along the way are rare, this will most likely finish on the first try. Now, this is not to say that we shouldn't take steps to correct errors at any one of these stages. Error correction at lower levels can sometimes be an effective performance booster. And the trade-off here is based on performance, not correctness. So whether or not one should implement additional correctness checks at these layers depends on whether the amount of effort put into the reliability gains are worth the extra trouble. Another example where the end-to-end argument applies is with encryption, where keys are maintained by the end applications and ciphertext is generated before the application sends the message across the network. Now, one of the key questions in the end-to-end argument is identifying the ends. The end-to-end argument says that the complexity should be implemented at the ends but not in the middle, but the ends may vary depending on what the application is. So, for example, if the application or protocol involves internet routing, the ends may be routers or they might be ISPs. If the application or protocol is a transport protocol, the ends might be end hosts. So identifying the ends in the end-to-end argument is always a thorny question that you have to answer first. Now, when talking about the end-to-end argument, it is worth remembering that the end-to-end argument is just that. It's an argument, not a theorem or a principle or a law. And there are many things that have come to violate the end-to-end principle. Network address translators, which we'll talk about in the next lesson, violate the end-to-end argument. VPN tunnels, which tunnel traffic between intermediate points on the network, violate the end-to-end argument. Sometimes TCP connections are split at an intermediate node along an end-to-end path, particularly when the last hop of the end-to-end path is wireless. This is sometimes done to improve the performance of the connection because loss on the last hop lossy wireless hop may not necessarily reflect congestion, and we don't necessarily want TCP to react to losses that are not congestion related. Even spam, in some sense, is a violation of the end-to-end argument. For email, the end user is generally considered to be a human, and by the end-to-end argument, the network should deliver all mail to the user. Does this mean that spam control mechanisms are in violation of end-to-end? And if so, are these violations appropriate? What about peer-to-peer systems, where files are exchanged between two nodes on the internet but are assembled in chunks that are often traded among peers? What about caches and in-network aggregation? So when considering the end-to-end argument, it's worth asking whether or not the argument is still valid today and in what cases. There are questions about what's in versus out, certainly, and what functions belong in the dumb minimal network. For example, routing is currently in the dumb minimal network. Do we really believe that it belongs? What about multicast, mobility, quality of service? What about NATs? And it's worth considering whether the end-to-end argument is constraining innovation of the infrastructure by preventing us from putting some of the more interesting or helpful functions inside the network. In the third course, we'll talk about software-defined networking, which in some sense reverses many aspects of this end-to-end argument. A fairly pervasive violation of the end-to-end argument are home gateways, which often perform something called network address translation. Now, in a home network, we have many devices that connect to the network, but when we buy service from our internet service provider, we're typically only given one public IP address. And yet, we have a whole variety of devices that we may want to connect. Now, the idea behind network address translation is that we can give each of these devices a private IP address. Now, there are designated regions of the IP address space that are for private IP addresses. One of those is 192.168.0.0/16. And there are others which you can go read about in RFC 3130. Now, each one of these devices in the home gets its own private IP address. The public internet, on the other hand, sees a public IP address, which typically is the IP address provided by the internet service provider. When packets traverse the home router, which is often running a network address translation process, the source address of every packet is rewritten to the public IP address. Now, when traffic comes back to that public IP address, the network address translator needs to know which device behind the NAT the traffic should be sent to. So it uses a mapping of port numbers to identify which device the return traffic should be sent to in the home network. So the NAT, or the network address translator, maintains a table that says packets with the source IP address of 192.168.1.51 and source port 1000 should be rewritten to a source address of the public IP address and a source port of 50878. Similarly, packets with a source IP address of 192.168.1.52 and source port of 1000 should be rewritten to the public IP address and a source port of 50879. Then when traffic returns to the NAT to one of these addresses, the NAT knows that it needs to rewrite the destination address on the return traffic to the appropriate destination IP address and port that's in the private network. So for outbound traffic, the NAT device creates a table entry mapping the computer's local IP address and port number to the public IP address and a different port number, and replaces the sending computer's non-routable IP address with the gateway or the NAT public IP address. It also replaces the sender's source port with a different source port that allows it to demultiplex the packets sent to this return address and port. For inbound traffic to the home network, the NAT checks the destination port on the packet, and based on the port, it rewrites the destination IP address and port to the private IP address in the table before forwarding the traffic to a local device in the home network. Now, the NAT clearly violates the end-to-end principle because machines behind the NAT are not globally addressable or routable, and other hosts on the public internet cannot initiate inbound connections to these devices behind the NAT. Now, there are ways to get around this. There are various protocols. One is called STUN, or Signaling and Tunneling through UDP-enabled NAT devices. And in these types of protocols, the device sends an initial outbound packet somewhere simply to create an entry in the NAT table. And once that entry is created, we now have a globally routable address and port to which devices on the public internet can send traffic. Now, these devices somehow have to learn that public IP address and port that corresponds to that service. And this might be done using DNS, for example. It's also possible to statically configure these tunnels or mappings on your NAT device at home. Needless to say, even with these types of hacks and workarounds for NAT, it's clear that network address translation is a violation of the end-to-end principle because by default, two hosts on the internet, one in the home network and one on the public internet, cannot communicate directly by default.